Let's talk about p-values. Now, before your eyes glaze over, I promise this is not going to be some dry, boring stats lecture. In fact, I'm willing to bet you already understand the core idea behind them. You just use your gut instead of a formula.
Okay, let me ask you something. Imagine I flip a coin 100 times, and I get 90 heads. Is that coin fair? What's your gut telling you? I mean, come on, it's got to be screaming no way, right? Something is definitely fishy with that coin.
Well, guess what? You just did statistics. That gut feeling, that little question that popped into your head, hang on, if this coin was actually fair, what are the chances of getting a result this nuts? That is the exact logic behind p-values.
To make this official, scientists need a starting point. Think of it like a courtroom, innocent until proven guilty.
And that starting point is called the null hypothesis. It's the boring, default, nothing interesting is happening here assumption. For our coin flip, the null hypothesis is simple. The coin is fair. We assume it's a 50-50 shot, unless the evidence is just overwhelming.
So what is the p-value then? It's simply a number that measures how surprised we should be by our result, assuming that the null hypothesis is true. A really low p-value is like a giant flashing neon sign that says, "Whoa, this is super unlikely to be random chance." A high p-value is more of a shrug, like, yeah, that could happen.
All right, let's put this into practice. Let's say we do our experiment and we get 56 heads out of 100. It's a little more than 50, sure, but is it weird enough to be suspicious? Well, we run the numbers and the p-value for this outcome is 0.193.
So what does that mean? It means there's a 19.3% chance of getting a result this lopsided, or even more so, just by pure random luck. You know, that's almost a 1 in 5 chance. Not that surprising, really. We're not going to throw out our fair coin idea just yet.
Okay, round 2. Let's make it a little more interesting. Same experiment, but this time we get 60 heads. Now we're a bit further from our expected 50. The old surprise meter's definitely starting to tick upwards.
And yep, the math backs us up. The p-value takes a nosedive, all the way down to 0.032.
Okay, now we're onto something. A 3.2% chance? That's pretty rare. In most scientific fields, there's a sort of unofficial line in the sand at 5%, or a p-value of 0.05. Since our result is below that line, we can start to get properly suspicious. Maybe our initial assumption, our null hypothesis, is wrong.
But now, let's go all the way back to that first scenario. The one that made you immediately say, no way. 100 flips, 90 heads. What does the p-value look like for that?
It's pretty much 0. The number is so incredibly small that, for all practical purposes, it's nothing.
And this is the whole point in a nutshell. The odds of getting 90 heads from a fair coin are just astronomically low. So we don't look at that and think, wow, we just witnessed a 1 in a billion miracle? No, we think our first assumption must have been wrong. We confidently reject the null hypothesis and conclude that coin is biased. Simple as that.
So we've got the concept nailed down. But you know, this way of thinking isn't exactly new. The logic has actually been developing for hundreds of years.
It all started way back in 1710. A physician named John Arbuthnot noticed that for 82 years in a row, more boys than girls were born in London. He realized that was like flipping a coin 82 times and getting heads every single time. The probability was just vanishingly small. Then, over a century later, a guy named Simeon Poisson suggested we need some kind of critical value to decide when a result stops looking random. And finally, in 1925, the legendary statistician Ronald Fisher formalized the whole thing, gave it the name p-value, and suggested that 0.05 was a pretty convenient and useful cutoff.
Now, there is one little bit of nuance here that really depends on the exact question you're asking. Are you looking for any kind of difference, or a difference in one specific direction?
This is this idea of a one-tailed versus a two-tailed test. It sounds technical, but it's pretty straightforward. With our coin, we were doing a two-tailed test. We would have been surprised by 90 heads, but we would have been just as surprised by 90 tails. We were just asking, is the coin biased in either direction? But say you're testing a new drug to reduce swelling. You only care if it goes in one direction, down. You're not interested if it increases swelling. That's a one-tailed test. It focuses the math on just that one specific outcome you're hoping for.
Okay, enough theory. This is all great, but let's see how p-values actually work out in the wild. How are they used in a real scientific paper?
Let's dive into a study from the Medical Journal of Australia. The researchers wanted to know, could a smartphone app help patients manage their epilepsy better? They set up a classic randomized controlled trial. They took a large group of patients, gave half of them the app, and the other half, the control group, got the usual care.
Now take a look at this first table. This is super important. Before the study even starts, you have to make sure your two groups are basically the same. And here's the fun twist. In this kind of table, you actually want to see high p-values. See that p-value of 1.00 for sex? That means the gender balance was perfectly matched. A p-value of 0.94 for age means the tiny difference between the groups is totally expected by random chance. So these high p-values are great news. They tell us the comparison is going to be a fair fight.
But then, you look at the results after the study is over. This is where you want to see the opposite. You're looking for low p-values. And bingo, look at the total score. The app group scored way higher, and the p-value is less than 0.001. That is a tiny, tiny probability, which means this big difference is very unlikely to be just a fluke. Same goes for quality of life. The low p-values suggest the app had a real, statistically significant effect.
So let's just boil it all down. A p-value isn't some magic bullet. It's a tool. It's our surprise meter. It's a standardized way to help us decide if what we're seeing in our data is just random noise or if it's the signal of something real actually happening.
But this leaves us with one final and pretty important question. That 0.05 line in the sand, it is a bit arbitrary, isn't it? So if a study comes out with a p-value of 0.06 and it's not statistically significant, does that mean the finding is worthless? And on the flip side, if another study gets a p-value of 0.04, does that mean it's automatically true and a major discovery? The real answer, of course, is a lot more complicated than a simple number, and that's definitely something to think about.